Okay, so let's continue this example. In the first part of this example, we figured out the zero input response, and we also found the impulse response of the system. As we continue working towards finding the total response, the next thing we need to do is find the zero state response of the system. The zero state response, we know, is the convolution of the impulse response with the input, and that's why we wrapped up the last video of finding the impulse response. We needed to know what it was. So in this part of the problem, we need to actually evaluate this convolution. We were told what the input was in the problem. The input is the unit step function, so we need to find the unit step function involved with the impulse response, which is written right here, that we found at the end of the previous video. So really what it boils down to is just performing this convolution now. So I'm going to go ahead and use the distributive property of convolution. I can write this as u of t convolved with 2u of t minus u of t convolved with e to the negative t. So really what I have here are two different pieces. This is what I'm going to call part 1, and this is what I'm going to call part 2. Really I have two convolutions that I need to do. So let's go ahead and do the first one. So the first convolution, u of t convolved with 2u of t. By definition, that's the integral from minus infinity to infinity, u of tau, 2 of u, t minus tau. And then the key is being able to sketch these different pieces. So here's my tau axis. The first quantity written in blue right here is just the unit step u of tau. It just turns on at time 0 and it goes for forever to the right. And then think about what the quantity 2u of t minus tau. That is a time reversed and shifted unit step. Since it's time reversed, it goes forever to the left side, and the shift amount is where it turns off t. So this is kind of the cartoon that I have for this convolution. If I look at this, I can see what's going to happen. Anytime t is less than 0, there will be no overlap, right? Its edge would be over here. So when there's no overlap, I get a product that's equal to 0. So for t less than 0, I get 0. But when t is greater than 0, then I get this overlap right here. They overlap from 0 to t. So if I integrate the product 2 times 1, which is 2, if I integrate 2 from 0 to t, I just get 2t, right? The area right here of this rectangle, its height is 2, and its width is t, so that's an area of 2t. So that's what I get for t greater than or equal to 0. I've written it here kind of piecewise. Well, I can rewrite that using the unit step to turn it on at time 0. I can write this convolution as 2t u of t. So that's the first convolution we need to do. The next convolution that we need to do is u of t convolved with e to the negative t u of t, which again by definition is the integral from minus infinity to infinity, e to the negative tau u of t minus tau. So here, remember, we can write convolution in any order. I've chosen to flip the unit step because I think it's going to be easier to time reverse that. So if I draw my tau axis, here is e to the minus tau u of tau, and then the time shifted and reversed unit step looks something like this again. It will turn off at time t. If t is over here, there's no overlap. So again, when time is less than 0, I get no overlap. So this product is 0. So its integral is equal to 0. When t is greater than 0, I get an overlap on this region. So I'm actually going to need to do the integral from 0 to t of my unit step, which is 1, times this function right here. So I get e to the minus tau d tau. So I just need to do this integral, which is very simple. That turns into just minus e to the negative tau, so that minus sign right there. We have to evaluate it at t and 0. So this turns into 1 minus e to the negative t. So up here, doing the integral was very trivial because it was just a rectangle. We could just look at it and get the area. Here, the overlapped was a function that we had to integrate. It was still a simple function. And this is the result of the integration. So now we know what goes right here for t greater than or equal to 0. Again, this is piecewise. Since it's piecewise with something happening at 0, I can use my unit step function and write the resulting convolution like this right here. So we now know what these two pieces are. I know what term 1 is. I know what term 2 is. I can go ahead and write those down and combine them to find the zero state response. The zero state response is the first part, 2t u of t, minus the second part, which was 1 minus e to the negative t, that quantity, times u of t. So that is my zero state response. I'm going to go ahead and factor out a u of t since it's common to everything. So that's my zero state response. All right, we're ready to put all of these things together. What is the total response of the system? The total response of the system is the zero input response plus the zero state response. In the first part of this example, we figured out that the zero input response was quantity 2 minus e to the negative t u of t. In this video, we figured out that the zero state response was equal to this quantity right here. And note that we can combine some like terms. I have a 2 sitting here and a minus 1 sitting here, so I can combine that to a 1. I have a minus e to the negative t and a plus e to the negative t, so those are going to cancel, and I'll just be left with the 2t. So combining like terms, this is what I get for the total response. So that completes this example. Doing the total response computation involves just about everything that we've been practicing in this chapter of material. You need to know how to find the zero input response. You need to know how to compute the impulse response. You need to know how to do convolution to compute the zero state response. And then you need to know that for a linear system, the total response is the combination of the zero input response and the zero state response. So lots of pieces. Just break it down into each part and work through each part carefully.